All right, when we get done with this section, we will identify characteristics of data set that is normally distributed, apply the empirical rule, compute z-scores and use them to compare values from different data sets. And we'll be using our calculator to find probabilities and percentiles. We're not going to use a table. The table used to be used before the calculator. That's that dinosaur thing nowadays. Now that we have a machine, a calculator that can help us out. All right, and I did also attach two calculators on our main dashboard, our Canvas core site, the normal calculator and the inverse norm calculator. We'll show you how those things work. All right, there's many things in the real world, ladies and gentlemen, that follow a normal distribution. Our people's heights follow a normal distribution. If you were to go out and measure all the lengths of the pine needles on a pine tree, you would discover that those lengths follow a normal distribution. A normal distribution is a symmetric distribution. So nature seems to opt for and love symmetry for some reason. The normal distribution is also used a lot in quality control in industry. They make use of the normal probability distribution to make sure that parts are within specifications before they're shipped out to the vendor. All right, so what does a normal distribution look like? Well, it looks like this right here. If you were to make a frequency histogram, you would expect the frequency histogram to look like this for a normal distribution. And we say this normal distribution is bell-shaped because it looks like a bell. So that's what a normal distribution looks like. A normal distribution is perfectly symmetric with respect to the mean, median, and mode, which are all right in the middle here. That means if you fold this graph about the vertical axis, it'll mesh up perfectly with the graph on the left side, et cetera, et cetera. Okay. Here are some properties that all normal distributions adhere to. The value right in the middle of the normal distribution is the mean, which is approximately equivalent to the median and also equal to the mode. So the mean, median, and mode for a normal distribution are approximately, if not exactly, equal to each other. The distribution is symmetric about the mean. This means that the graph has two equal halves, one to the right and one to the left of that vertical line I showed you. And so the right side is a mirror image of the left side and vice versa. Areas we're going to discover are the same thing as probabilities or percentages or proportions. The total area underneath the entire curve is 1. Okay. So if you go from negative infinity all the way up to positive infinity, you would discover that the area underneath the entire curve is 1. And that is a requirement for any probability distribution, whether discrete or continuous, is that the sum of the probabilities of all events of an experiment must always sum up to 1. Another thing about a normal distribution is the graph is asymptotic with respect to the horizontal axis, which means that the graph will get closer and closer and closer to the horizontal axis, but will never touch or never, ever, ever, ever cross this horizontal axis. Okay, we say the horizontal axis is a horizontal asymptote to the graph. And that's also true if you go to the left forever. The graph gets closer and closer to the horizontal axis, but never touches or crosses it. So all normal distributions adhere to those properties are. All right, now areas underneath this normal distribution curve here are really going to be the same thing as probabilities, as we're going to find out. And how do we find the areas underneath this curve here, this normal distribution? Well, unfortunately, the function that generates this bell-shaped curve graph is a natural base exponential function. that looks like this, e raised to the negative x squared power. That is not an elementary function, ladies and gentlemen. And in order to find areas underneath this curve, you would have to use numerical integration from calculus to approximate these areas. But we're not going to use calculus in here. That's not what this course is about. To the rescue is a marvelous calculator, not our TI-30XS that cannot compute areas underneath the normal distribution. But if you go into Math 150, elementary statistics here at Mott in the future, the TI-84 calculator can compute areas underneath the normal distribution curve. The TI-30X cannot. I did attach 2 calculator links on our Canvas course site, a normal calculator, which will enable us to compute areas underneath this curve, and an inverse norm calculator, which will enable us to find values on the horizontal axis called percentile values. Okay. All right. All right, now example 1, getting information from a normal curve. What is the mean height? Well, the mean height is 63.7. That's the mean, median, and mode of this normal distributed data here, 63.7. What percentage of women are between 57.4 and 59.1 inches tall? That would be 3.4% of all women have a height between 57.4 and 59.1 inches. You see this normal distribution here represents all the heights of women in the United States. So the average height of all women in this country is 63.7 inches, which if you divide that by 12 inches per foot, it gives you something a little bit more than 5 feet, okay? 3.4% of all women have heights between 57.4 and 59.1 inches. About 30.3% of all women's heights lie between 63.7 inches and 66 inches. Okay. So these areas are really proportions or percentages or probabilities. Because I could ask myself, what's the probability that if I randomly select a woman in the United States, that her height will be between 57.4 and 59.1 inches? The answer to that question would be the probability would be about 3.4% or 0.034. So areas are equal to probabilities. Now in C, it says, if there are 31,806 women at a stadium concert, how many of them would you expect to have a height between 63.7 and 66 inches? Well, we would expect about 30.3% of those women to have that height between 63.7 and 66 inches. So in order to determine how many of these 31,806 women have that height within those two values, you'd have to take 30.3% of this. Now, how do you take a percent of a number? Change the percent to a decimal by shifting the decimal point 2 places to the left, so 0.303. And then you'd have to multiply it by 31,806 women. Go ahead and do that, and somebody tell me, of the 31,806 women, how many of them would be expected to have a height between 63.7 inches and 66 inches? Somebody dial that up and tell me.
I have 99,637.218.
So about 9,000 some women, correct? At that,
Yes.
at that stadium would be expected to have a height of about 63.7 inches and 66 inches. Okay. All right, now, ladies and gentlemen, we're going to run into an extremely important rule called the empirical rule. This empirical rule enables you to do inferential statistics, which unfortunately we don't have time to do in here. But if you get into Math 150, the first formal elementary course in statistics here at Mott, you will get into inferential statistics and have to rely on this empirical rule to build what are called confidence intervals and to also do hypothesis testing, okay? All right, when data are normally distributed, approximately, according to this empirical rule, approximately 68% of the values will be within one standard deviation of the mean. About 95% of the entire data values will be within two standard deviations of the mean. And approximately 99.7% of all your data values in your data set will lie within three standard deviations either side of your mean. Pictorially, that is represented here. So this picture basically embodies what's called the empirical rule. Remember, the mean, median, and mode of the normal distribution is right in the middle here. So this is your mean. By the time we venture from one standard deviation below your mean, x bar minus 1 times your standard deviation, to one standard deviation above your mean, x bar plus 1 times your standard deviation, the empirical rule guarantees that in this interval here, about 68% of your data will lie. By the time you venture two standard deviations either side of your mean, from two standard deviations below the mean, x bar minus 2 times s, to two standard deviations above your mean, x bar plus 2 times s, we would expect about 95% of our data points to lie in this interval between these two endpoints. So 95% of our data lies in this larger interval. Finally, by the time you venture three standard deviations either side of your mean, that is to say, x bar minus 3 times your standard deviation s to x bar plus 3 times your standard deviation s. In this larger interval, the empirical rule guarantees that about 99.7% of your data values lie. That's pretty much your entire data set. This is called the empirical rule. Sometimes it is referred to as the 68-95-99.7 rule. Now, in certain stats textbooks, some stats textbooks have 99% lying, three standard deviations either side of your mean. Some stats textbooks I've seen have 99.9%. This one has 99.7%. Safe to say that bare minimum, there's at least about 99% of your observations in that interval. That's the empirical rule. And notice the perfect symmetry that exists with this empirical rule. Notice that from one standard deviation below your mean to the mean, half of 68% or 34% of your observations would lie in this interval. And by symmetry, we would then expect 34% of your observations to lie between your mean and one standard deviation above your mean. So we have perfect symmetry here. We would expect 13.5% of your observations to lie between two standard deviations below your mean to one standard deviation below your mean. Likewise, 13.5% of your observations will lie between one standard deviation above your mean to two standard deviations above your mean. .15% of your observations are greater than three standard deviations above your mean, and 0.15% of your observations are less than one standard deviation, or less than three standard deviations below your mean. Okay, so that's the empirical rule. So I would become familiar with this rule. It's gonna help you out when you do go to do some work on Alex. All right. Here's an example, according to the website answerbag.com. The mean height for male humans is 5 feet 9.3 inches with the standard deviation of 2.8 inches. If this is accurate, out of 1,000 randomly selected men, how many would you expect to be between 5 feet and 6.5 feet? Between 5 feet 6.5 inches and 6 feet 0.1 inches. All right, well, what we're gonna have to do, ladies, I'm gonna answer this question, is we're gonna have to convert these values here into what are called z-scores. Okay, so what is a z-score? A z-score is basically a measure of position for a data value. A z-score of a data value x is the number of standard deviations that x is from the mean. All right. Now, to find a z-score of a data value x is pretty simple. You take the data value x, subtract off the mean of the data set, and then you divide it by the standard deviation. So this is called a z-score formula. It computes the z-score for any data value x, provided that you know the mean of the distribution and you know the standard deviation from whence x was chosen. Now, to answer this question here, out of the 1,000 randomly selected men, how many would you expect to have a height between 5 feet 6.5 inches? Well, 5 feet 6.5 inches, I'm going to convert into nothing but inches. 5 feet is 5 times 12 or 60 inches. And what's 60 plus 6.5 inches?
$66.5.
Okay. I want to find a z-score now of this 66.5 inch measurement. To do that, I use my formula up here. So I replace x with 66.5. I'm going to subtract off the mean of this distribution, and the mean height for males is 5 feet 9.3 inches. Now 5 feet is 5 times 12 or 60 inches.
It'd be 69.3 inches.
69.3 inches, that's the mean. And we're going to divide it by the standard deviation height, which is 2.8 inches. All right, let's get on our calculator and find the z-score for 66.5. So let's do that. -1. I get -1. So what this is saying is it's saying, how do we interpret this z-score of -1? It's saying that 66.5 is one standard deviation, one standard deviation below the mean. It's one standard deviation below the mean. In a similar fashion, I'm going to standardize 5 feet, 6.5 inches, which is really what? Well, we've seen that 5 feet is really 60 inches, so it's going to be 60.
It'd be 66.5.
You know, plus 6.5 inches. It'd be 66.5 inches. Now we're going to find the, wait a minute here. Wait, I already did this one. What am I talking about? The other height is 6 feet, 1/10 of an inch. So 6 feet, 0.1 inches. Now 6 feet is 6 times 12 or 72 inches. Plus 1/10 of an inch is going to give us 72.1 inches. Let's find the z-score for 72.1 inches. So the z-score for 72.1 inches is going to be 72.1 minus the mean, which is 69.3. Divided by the standard.
I'm gonna go. I have an appointment.
Okay.
All right. Have a good day.
Yeah. Now I'm going to divide this by 2.8. And that gives me one standard deviation. So we interpret this as saying 72.1 is one standard deviation.
Where did you get the 6 feet 1 inches at?
All right,
Or, I mean 0.1 inches.
that's coming from this word problem here. See it? This example 2. 6 feet, 0.1 inch. So they want to know how many of these 1,000 randomly selected male humans have a height between 5 feet, 6.5 inches and 6 feet, 1/10 of an inch. Well, ladies and gentlemen, we need to understand that 5 feet, 6.5 inches and 6 feet and 1/10 of an inch actually lies between -1 and 1 standard deviation above the mean. What did the empirical rule guarantee? What percent of the observations lie 1 standard deviation on either side of your mean? Do we remember? The empirical rule guarantees that 1 standard deviation below your mean to 1 standard deviation above your mean, 68% of your observations lie. Therefore, we can now answer this question. Because we know that 68% of the 1,000 randomly surveyed males must have a height that lies between 66.5 inches and 72.1 inches. So how do you take 68% of 1,000? Change the percent to a decimal, shift decimal point 2 places left, drop percent symbol, multiply it by 1,000. The answer is 680. So we would expect 680 of these 1,000 randomly selected males to have a height between 66.5 inches and 72.1 inches.
Now, how did you get the 68%? Was that on the graph thing?
You get to what percent now?
The 68.
Yeah, the 68%, that's the empirical rule. The empirical rule says that once you venture 1 standard deviation below to 1 standard deviation above your mean, you would expect 68% of your data to lie in this interval right here. See that? 68%. By the time you wander 2 standard deviations either side of your mean, 95% of your data lies in this interval. By the time you stray 3 standard deviations either side of your mean, about 99.7% of your observations will lie in that larger interval. And that's the empirical rule. That's what it guarantees. Oh, is that making any sense there?
That deck's too low for the backyard.
Yeah, well, if. All right, that problem make any sense there? This problem here. $680 men. Now, there's an infinite number of normal distributions with an infinite number of means and standard deviations. But there's one, the most important one, at least it used to be the most important one before calculators were invented, was the standard normal probability distribution. And the standard normal distribution is a normal distribution. So enjoys all the attributes we spoke of it in the past. But the added thing with the standard normal distribution is that the mean is always 1. The mean is all, let's see. So the thing that's always true about a standard normal distribution is that the mean is always 0. The mean is always equal to 0, and the standard deviation is always equal to 1. So X bar is always equal to 0, and the standard deviation is 1. It's always true for the standard normal distribution. So you can see right here that this is your mean. X bar is equal to 0. And you can see that this is 1 standard deviation above your mean, 1 standard deviation below your mean. Good. So that's what characterizes the normal distribution from the standard normal distribution is the mean and the standard deviation. This is the formula to compute a z-score, but we already mentioned that. And again, a z-score is the number of standard deviations that a data point wanders away from the mean. Okay, now based on the information in example 2, find the z-score for a man who is 6 feet 4 inches tall and describe what it tells. Well, how many inches are in 6 feet? Well, 6 times 12, last time I checked was 72. 72 inches plus 4 inches would be 76 inches. They want us to find the z-score for 76 inches for this particular distribution for the male heights. So to do that, we're going to use our z-score formula. We're going to take 76 inches, subtract off the mean of the distribution, which is 69.3 inches, and we're going to divide by the standard deviation S, which is 2.8 inches. That gives us a z-score of 2.40. So that means that we can say that 6 feet 4 inches is 2.4 standard deviations above the mean of all other male heights. So notice that somebody's that is this tall would probably stand out for most people. All righty. And somebody that is that tall should maybe be thinking about joining basketball. Do you agree? That's pretty tall, 6 feet 4 inches, although there are taller people. Okay, now. This is another area where Z-scores come in very handy. As you probably know, there are two main companies that offer a standardized college entrance exam, the ACT and SAT. Usually you have to take those exams before you gain entrance into a university. Since each has a completely different scoring scale, it's really difficult to compare the scores of students that took the different exams. It's like comparing apples and oranges. One year, the ACT had a mean score of 21.2 and a standard deviation of 5.1. That same year, the SAT had a mean score of 1,498 and a standard deviation of 347. All right. Suppose that a scholarship committee is considering two students, one who scored 26 on the ACT and the other who scored 1,800 on the SAT. Both are pretty good scores, but which one is better? See, ladies and gentlemen, it's really difficult to compare which score is better because these two different exams had two different means and two different standard deviations. And so it's like trying to compare, like I said, apples and oranges. It's just not happening here. Our only hope is to level the playing field by converting these scores into what are called Z-scores. And then we'll just compare the Z-scores to see which item is further to the north. To see which item is the better score. That's what I meant to say. Okay. So we're gonna have to take the score of 1,800 and standardize it, and also 26 and standardize it, turn them into Z-scores. First, let's take 26 and turn it into a Z-score. That's gonna be 26 minus the mean of the ACT scores. The mean they told us was what, 21.2? Divide that by the standard deviation score, which is 5.1. That gives us a Z-score of 0.94. The 1,800 score from the SAT, we want to standardize that or find the equivalent Z-score for it. We take 1,800 minus the mean of the distribution. And what's the mean? All right, so 1,800 minus the mean of the SAT scores was 1,498. Divided by the standard deviation score of the SAT scores, which was 347. We get a Z-score of 0.87. Well, ladies and gentlemen, the Z-score that is furthest above the mean would be 0.94 here. And that corresponded to the so the ACT score is a better score because 26 is further above the mean for that exam as opposed to the SAT score, which is only 0.87 standard deviations above the mean. So the person that scored 26 on the ACT did a better job than the person that scored 1,800 on the SAT. All right. Now, here are two very important things about the standard normal distribution curve. Remember, the mean is 0 and the standard deviation is 1 for such a distribution. I'm going to try to draw the standard normal distribution here. All right, here's the standard normal probability distribution here, with the mean again as being 0. There's one standard deviation above your mean, and there's one standard deviation below your mean. Notice the upper half of the curve constitutes half of the area. Remember, the entire area is 1. So the upper half of the curve would have an area of 0.5. And notice the area or the proportion or the probability to the left of the y-axis is 0 point. So we would expect to have 50% of the area also occur below the mean. Okay. All right. Now the area between 0, the mean, and any positive z-score is equal to the area between 0, the mean, and the same z-score, only negative z-score. So there's the same amount of area in here. Okay. Well, let's go on here. All right. Now, for these examples here, they want us to compute the area under the standard normal probability distribution curve between two z values. And I'm going to show you how to use this calculator to do that. So they want us to find the area between $1.55 So let's see, this is 1.55. It's above the mean of 0, and 2.25 would be up here somewhere. So to find the area between these two values here, underneath the standard normal distribution curve here, sometimes we call it the z distribution. You have to find this area underneath this curve here. So between those two z values, we're being asked to find this area here, which is this shaded area here. Okay, that's the same thing. This area is the same thing as saying the probability that z lies between 1.55 and 2.25. This area is equal to this probability. Now, how are we going to do that? Well, we're going to need a calculator to help us out. And ladies and gentlemen, I'm going to go show you our calculator on our Canvas course site here.
It's too late. It's almost done.
All right, so let's go to our Canvas course site. And on our main dashboard, we have this calculator called the normal calculator. I'm going to click on it, scroll upwards, and here it is. Now, to use this calculator, we're going to have to type in the lower bound of our interval and the upper bound and mean and the standard deviation. So what interval is the interval of interest for us wanting to compute this area or this probability? Well, the interval has a lower bound of 1.55 and has an upper bound of 2.25. So this is going to be your lower bound, and this is going to be your upper endpoint or upper bound. Okay, so let's go type in on our calculator 1.55 for the lower bound. And for the upper bound, let's type in 2.25. Now we need the mean and the standard deviation of this data set. The mean, since it's the standard normal distribution, is always 0. And since it's the standard normal probability distribution, the standard deviation is always 1. So we populated our fields. Let's go down and calculate. And boom, we're done. So then on the area between 1.55 and 2.25 is right here, 0.0483. That is the area. That is the area or the probability. So again, this area or probability is 0.0483. Everybody understand how we just use that calculator there? So this area constitutes about 4.8% of the entire area of the entire curve. Does that make sense how we use that calculator to compute this area? All right. Go back to our PowerPoint. I'm looking at another one now. Now in B, they want you to find the area between Z is equal to negative 0.60 and Z is equal to negative 1.35. So negative 0.60 being less than 0 is going to be to the left of the mean a little bit, and negative 1.35 is even further to the left of the mean of the standard normal distribution. So therefore, they want us to compute this area here between negative 0.60 and negative 1.35. This area is really equal to computing the probability that Z lies between negative 0.60 and negative 1.35. All right, so we got to find this area here. So our lower end point of our interval is going to be what? Negative 1.35, and the upper end point of our interval is negative 0.60. Take these to your calculator. Let's go to our calculator at our Canvas course site. Type in the upper bound or the lower bound, which is negative 1.35. The upper bound is going to be negative 0.60. The mean of our distributions being still the standard normal distribution is 0, and the standard deviation is still 1. Calculate, and boom, there is the area. So here's your answer. So that area between those two Z values, whoops, that area there is going to be about 0.1857. So it's that is our area. 1857. So this area is about 1.9% of the area of the entire curve here. And I do have this exaggerated. These values are actually a lot closer to each other than I have here. Okay.
On that first question that you did, why was the lower 1.55?
1.55. Because they wanted us on our PowerPoint to compute the area between 1.55 and 2.25. You see that?
Oh, I was thinking that was a 6. Okay, never mind.
Yeah. All right, now let's try C. Try to find the area between positive 1.50 and negative 1.75. And again, we will make use of our calculator. I always recommend graphing and shading the area so that you have an understanding as to what area you're being asked to find here. Again, it is a standard normal distribution. I'll be honest with you, ladies, and whenever you see Z as the random variable, it's always your Z distribution, which is always your standard normal distribution, which is always the normal distribution that is a mean of 0 and a standard deviation of 1. All right, so between negative 1.75 and 1.50. So negative 1.75 is going to be down here, and positive 1.50 is going to be like up here. They want us to find this area here. This area is really equal to the probability that Z lies between 1.50 and negative 1.75. So let's go to our calculator, where our lower end point is negative 1.75 and our upper end point is 1.50. So we take this to the calculator. The lower end point is negative 1.75. The upper end point is 1.50. The mean is still 0 and the standard deviation is still 1, since it's still our standard normal probability distribution. Click on calculate and boom, you have the area. So the area between those two Z values is 0.8931. That is the area. So therefore, about 89.31% of the area of the entire curve lies between negative 1.75 and 1.50 for the standard normal distribution. That's your area, or that would be equal to this probability. Is this making sense how we're computing areas underneath the standard normal distribution curve by using that calculator? Making sense here so far. You know how areas are really probabilities. All right, I have one now. Suppose that I want you to find the area for Z greater than negative 1.75. Well, this area really is equal to this probability. The probability that Z is greater than negative 1.75. Diagrammatically speaking, that's going to be what area here? That's going to be this area here. And it goes forever to the right. Well, the lower end point of this interval is negative 1.75. The upper end point of this interval, ladies and gentlemen, is called positive infinity. Now, we don't have positive infinity to type in for the upper end point of this interval. And because of that, this application says that for positive infinity, you are to type in 1e99. What in the world is 1e99? E stands for exponent. 99 is the exponent. You know what this is equal to? This is equal to 1 times 10 to the 99th power, which means there's 99 zeros after the 1 here. Wake me up when I've listed 99 zeros. 1, 2, 3, 4, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 2, 3, 4, 5, 6, 7, 8, 9, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. Wait a minute, I got to go up to what, 99 zeros? I'm only at 50. How about dot, dot, dot? Ladies and gentlemen, if you had this amount of money in your bank account right now, would you be here today? Right here. You know, I hear deathly silence out there. That indicates to me that one of two things is going on here. A, either all of us do have this amount of money in our bank accounts, or B, we're out playing golf. It's got to be one or the other. I'm not going to guess which one. But ladies and gentlemen, is this a big or small number? What do you think? Anybody that's out there? Big or small number?
A very large number.
That's a very, very large number. This makes Elon Musk look like what? A pauper in rags. Do you agree? A pauper. Correct? This makes anybody on planet Earth look like a pauper when it comes to money, ladies and gentlemen. This means a very big number. This, for all practical purposes, we will use to simulate positive infinity, although this itself is dwarfed by the size of positive infinity. Negative infinity, if we ever run this away to the left forever, will be simulated by typing in negative 1E99. Is this making sense here? Because this guy would be equal to negative 1 times 10 to the 99th power, which is negative 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2, 3, 4, 5, 6, 7, 8, 9, 30, 1, 2, 3, 4, 5, 6, 7, 8, 9, 40. Dot, 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 all the way up to 99. That's an extremely small number. That's extremely far to the left on the z-axis. Okay? We call that, for all intents and purposes, negative infinity. I'm trying to compute this probability. I'm trying to find this shaded area here. Therefore, ladies and gentlemen, my lower endpoint is negative 1.75. My upper endpoint is positive infinity, which I'll have to type in this. Let's take this to our calculator. All right, what's the lower endpoint? Negative 1.75. We're good there. We don't have to change that. Upper endpoint has got to be positive infinity. Hey, if you forget, look at, they remind you here. See the reminders here? Look at that. Isn't that nice to have that little reminder in case you forget? So positive infinity is to be simulated as 1 uppercase E99. The mean and standard deviation are still 0 and 1 respectively, being the standard normal distribution. Go to calculate. Boom. There's your area. So ladies and gentlemen, 0.9599 is that shaded area. Do you agree that's pretty close to 1? That's pretty much the entire what? Area of the entire curve. Do you agree? Almost the entire area. So this probability is 0.9599. That's what this area is here. Almost 1. I have a question. How would you find the area of the lower tail down here? Anybody? How would we find the lower tail area? How could we do that? Knowing the upper tail is 0.9599. How could I find the lower tail area? Well, you could subtract the 0.9599 from 1. That would give you the lower tail area. All right. This calculator making any sense, ladies? Suppose I wanted to find the area for z less than 0.98. Diagrammatically speaking, that would be what shaded region? Well, the mean of the standard normal distribution is 0.98. Is bigger than 0. That's almost 1 standard deviation above your mean. So it's be about right here. I'll call that about 0.98. And we want Z to be less than this value. So we're talking about this shaded area down here. Therefore, what's my interval? What's my left endpoint of this interval? The left endpoint is negative infinity, which is negative 1e99. The upper endpoint of this interval is 0.98. Let's take this to our calculator now. Take this to our normal calculator. Whoops. Oh, that's that Geico. I don't know if that's good. What's the lower endpoint? Negative infinity? Negative 1e99. What's the upper endpoint? 0.98. Mean and standard deviation are still 0 and 1 because all we have talked about so far today is the standard normal probability distribution. In 2 days, ladies and gentlemen, we'll talk about other normal distributions that have other means and other standard deviations. But today, it's just the Z distribution. Let's click on calculate now, and boom, there's your area. So the area is 0.8365. That's really the probability that Z is less than 0.98. I just found that probability to be 0.8365. That means about 83.65% of the area of the entire curve is this shaded region here. Any questions, ladies and gentlemen, how we're computing areas underneath the normal probability distribution using our normal calculator, again, which is on our main Canvas course site dashboard. The link's there.
Will we actually have to do this part on Alex?
Alex, yes. On Alex, make sure you have, your Canvas course site opened up so that you can use that calculator, okay? Hey, you guys are lucky because the exam that I give you enables you to use this calculator. My face-to-face classes, we don't have access to this calculator because we don't all have laptops. And so I have to deprive them questions like this on their exams. I cannot ask questions like this on their exams. So you guys are actually getting more for your money. Isn't that awesome? Think of it that way. You're getting more for your money. Somehow I'm not feeling the love out there. But you are, ladies and gentlemen, you are getting more for your money because I can ask you these questions where I cannot ask the face-to-face people because they don't have a calculator to compute these areas like we have at our disposal. Oh, don't get me wrong. They still do Alex outside of class. So they still have questions like this, but I also give them an in-class exam and quiz too. And I take the average of that coupled with their Alex quiz and exam to give them a final quiz and exam score. So actually the face-to-face meetings are a little bit more strenuous than these here because you just have to deal with your Alex. That's it. I don't give you an actual paper exam or paper quiz like I do the face-to-face people. All right, how did I get on that topic? Oh yeah, this normal calculator is pretty cool, isn't it? All right, see how this is working here? Okay, that's great. Now this is just showing you, ladies and gentlemen, how to use the Z table in the back of your book to compute these areas. I'm not going to go over the Z table. In all honesty, it is a dinosaur concept because we have our calculators available nowadays. And so I really think those tables are rendered obsolete. Used to use them in the old days, but not now. All right. Hey, if you get into the Math 150 class, the TI-84 calculator has a normal CDF function, which enables you to type in the lower endpoint, upper endpoint, the mean and standard deviation of the distribution, and it will crank out areas underneath the normal curve for you. Unfortunately, our TI-30XS does not have the normal CDF function. That's a drag. You'd think they'd put the thing in there, but they didn't. So. All right. So this is just stuff pertaining to normal, the TI-84 calculator. You don't have to worry about this stuff here. That's just technology stuff. All right, hey, let's go to our textbook now and see if we can have some fun in the remaining time. Okay, so away we go. All right, here's our textbook here. Boy, aren't we going to miss this textbook? What are we going to do without this class in 2 days, Lego? What are we going to do? All right. We're going to be lost. All right, let's go to section 11.6. Somehow I think we'll find some things to fill our time in. All right, here we go. 11.6. As always, you know, it's always a wise thing to look through your sections, look through the examples and stuff. If you haven't done that yet, don't worry about it. It's way too late now anyways, but keep that in mind for future classes. It's always wise to look at some of the examples, your sections. All righty. Let's see if we can have some fun here though. Let's see here. What do they want us to do? The mean, let's see. I'm not sure what they want us to do with that. This is 11.6. Yeah, okay. All right. I want you guys to, using the normal calculator, by going to the Canvas course site, clicking on the main link, normal calculator. I want you to compute some areas underneath the Z distribution for me. I want you to do these problems here. Classwork number 1, number 27, 29, and number 30. Compute all those areas using your calculator. I would also recommend to draw a little picture. For instance, this first one here. Let's actually draw a picture of the standard normal distribution, which looks like this, a bell-shaped curve. They want the area between 0. Well, 0 is the mean of the standard normal distribution. So they want the area between 0 and negative 0.5. Negative 0.5 is a half standard deviations below the mean. That would be down here at negative 0.5. So they want the area, they want this shaded area here. Okay, go ahead and see if you can compute that area and then do 29 and 31 also. Classwork 1. All right, so number 27, they want you to find the area between negative 0.5 and 0. So the lower end point is going to be negative 0.5, upper end point will be 0, the mean is 0, standard deviation is 1. And that's going to be the mean and standard deviation of all these, because all of these refer back to the standard normal probability distribution. So using our calculator, we should be able to crank these out. So lower is negative 0.5. Upper endpoint is 0. Calculate, and you get the area as being 0.1915. 0.1915. Next one, the lower endpoint of this interval is 1. The upper endpoint is positive infinity. So 1E99. Upper endpoint is 1E99. Calculate, and you get the area as being 0.1587. Now they want you to compute this area here, which is really this probability as Z is less than negative 0.40. The lower endpoint is negative infinity. Type this in. Upper endpoint is negative 0.40. Mean is 0, standard deviation is 1. So when you go to your calculator, the lower bound is negative infinity, so negative 1E99. The upper bound is negative 0.40. The mean and standard deviation are 0 and 1 respectively. Click on calculate and you get your answer. So this probability here is 0.3446. And hopefully you're getting those probabilities and you know how to use that calculator there.
So when you're like on 29, when you did like to the right of 1.0, you use that as the upper and then I mean as the lower, and then what was the upper value?
Positive infinity. Because that shaded region goes up to positive infinity to the right forever. If you go to the right forever, you're always going to positive infinity. If you go to the left forever, you're always going to negative infinity. And this one is just between 0 and negative 0.5. So. All right. So we're seeing how we're computing area underneath the curve here, the normal distribution curve, the standard normal distribution curve. And these areas are, like I said, they're really equivalent to probabilities. So they're one and the same with probabilities. All right. Now, the only other thing that I want to show you is what if we ask ourselves a different question now? What if we ask ourselves this question? What Z value has an area of 0.91 below it? Now, this is asking a different question. Up to this point, we've been given the Z value and being asked to compute the area, but now we're given the area and we're being asked to find the Z value. So 0.91 of the entire area of the curve means that this Z value is going to be way up here somewhere. And we got to find the Z value here now, below of which lies 91% of the area of the entire curve. So now we know this area is 0.91. They want us to find the Z value here, which is really the 91st percentile. That's really what it would be called, is the 91st percentile, because 91% of all the other observations are below this Z value. Well, we cannot use our normal calculator anymore. We have to use another calculator called the inverse norm calculator. And we do have that calculator link on our Canvas course site. Oh, you know what? I haven't put it there yet, but I will. So I'll show you what it looks like. I will put a link on our main Canvas dashboard. It's called the inverse normal calculator. It enables us to find percentiles, okay? So we really want to find the 91st percentile here. So we're gonna have to use this inverse normal calculator. Let's click on it. I will put the link on our main dashboard. It's not there yet, but it will be. Just click on it. And it takes you to this calculator here called the inverse normal calculator. Now, ladies and gentlemen, we have to enter the area between 0 and 1 to the left of the unknown Z value. Now, our area is 0.91 because they told us that. The mean of this distribution is 0, and the standard deviation is 1, since it's a standard normal distribution. So all we have to do is click on calculate, and it will give us that Z value, or the 91st percentile. Click on it, and your 91st percentile would be 1.34. There's your answer. This is not a probability. This is a Z value on the horizontal axis. Remember, probabilities are always between 0 and 1. So this is obviously not a probability. No, what it is it's saying that this Z value must be 1.31 up here. It is the 91st percentile, because 91% of the area of the curve lies below it. Okay. Oh, that should be 1.34. Sorry. That was 1.34. Okay, that's your 91st percentile. All right, let's try another one. Suppose I want to find the 47th percentile. In other words, I got to find a Z value below of which lies 47% of the area of the curve. Well, since it's less than 50% of the area to the left, it has to be a Z value not to the right of the mean, but to the left, slightly to the left. We want to find a Z value below of which lies 47% of our area of our curve here. So how are we going to do that? Well, we're going to go to the inverse norm calculator. That same calculator, we're going to type in the area to the left is 0.47. The mean is 0, and the standard deviation is 1. And we'll get the Z value here. Yeah. So let's take this to our calculator. Type in the area to the left of our unknown Z value we seeketh as being 0.47. The mean and standard deviation are 0 and 1 respectively. Click on calculate. Boom, you got your answer. So that Z value has to be negative 0.08. So there you go. This has to be negative 0.08, below of which lies 47% of the area of the curve. So this is your 47th percentile, negative 0.08. This is making sense here while we're finding percentiles here. All right. What if I give you a problem like this? Standard normal distribution. And this area is 0.53. How are we going to find this unknown Z value? Why can I not type in 0.53 into that inverse norm calculator? Why can I not do that? Because, ladies and gentlemen, the calculator doesn't work that way. Notice this calculator says it must be an area to the left of the unknown z value, to the left, never to the right. So how can I remedy this situation? How can I find an unknown z value using this calculator if I don't have the area to the left? Anybody? How can I find that area to the left? Well, let me give you a little hint. What's the area underneath the entire curve? Did I hear somebody whisper 1? I think I heard that. 1 it is. So how are we going to find this area to the left of our z value? If this area to the right is 0.53, what does that leave us for the area to the left?
One minus 0.53.
1 minus 0.53, which will render what? By the way, what's wrong with my diagram? There's an error here. What's wrong? That picture's not right. That picture's messed up. Why?
50 isn't the mean.
Well, the mean is 0. You know, the mean is down here. What's wrong with my area here? That's not right. No good. It's no good. Because what's the area of the curve to the right of the mean? What's this area? That's only the upper half. That area should be what? .50. How can this be greater than 0.50? If this z value is to the right of the mean, it's impossible. No, didn't draw it correctly. Should be drawn like this. There we go. There's your z value. Because now this area could be larger than 50%. Do you agree? 0.53. So what is the area to the left then? The area to the left here is going to be 1 minus 0.53, which is something less than 50%. Namely 0.47 or 47%. So that's what we take to our inverse norm calculator. We take the area to the left as being 0.47. The area is 0.47. The mean is 0. Standard deviation is 1. Calculate, and we get negative 0.08. So there's your answer. So therefore, the area to the right of negative 0.08 must be 53%. The area to the left of negative 0.08 is 47%. Makes sense why this is negative because it's to the left of x equals 0, the mean. This z value, this 47th percentile, if you will, is negative 0.08. That's your 47th percentile. All righty. All right, so go back to our textbook. Let's see if you can do a couple problems down here now. All right, number 55, we'll call this classwork number 2. Find a z-value to the right of the mean so that 67.4% of the distribution lies to the left of it. You need to find a z-value, which would really be like the 67.4th percentile, 67.4 percentile value. Try to find that percentile value, 55, using the inverse norm calculator. Classwork number 2, number 55. All right, so we want to find this Z value here, below of which lies 67.4% of all the area of the curve. That's what we want to do. So since we're not trying to find an area or a probability, we're given the area to the left of the Z value. We're trying to find this percentile value. We use the inverse norm function. And we type in the area to the left of 0.6674. And the mean is 0, standard deviation is equal to 1. So let's go grab our inverse norm calculator. Here it is. Type in the area to the left, which is 0.674. Mean and standard deviation are 0 and 1. Calculate. And there you go. Wait a minute here. Something's wrong. The area to the left is 0.674, right? We should have a Z value that is greater than 0.5, shouldn't we? Sure we should. Because that's more than 50% of the area of the curve. That's 67.4%. So what's going on here? 674. 0.45. That wouldn't be right. Something's wrong. Let me try this. See, this one's better, 0.78. Let me try this, 0.674. All right, I think I might know what's going on here. Let's see. Let's see. Six, 7. Two point two eight, 0.28. It's not making any sense. Oh, wait. No, what am I thinking of? No, this is correct. 0.674. No, the answer should be exactly 0.45. So this Z value is 0.45. I had a brain fart there for a second. It should be 0.45. 0.45 is to the right of the mean because the mean is 0. And isn't 0.45 greater than 0? Yeah, so this is correct. Yeah, your 67.4th percentile would be 0.45. That would be your Z value there. Okay. All right, so today we basically introduced ourselves to the standard normal probability distribution called the Z distribution. We showed ourselves how to compute Z scores for a data point and how we could compare two different like exam scores to see which one is the better score by converting both exam scores to Z scores. We also introduced ourselves to the normal calculator and the inverse normal calculator, whether we are computing probabilities or areas. We would use the normal calculator, or computing percentile values, we would use the inverse norm calculator. In 2 days, we'll wrap up this course by applying the normal distribution to two application problems, where we'll look at normal distributions that have different means and standard deviations, and we'll answer application questions, trying to find probabilities by computing areas for those normal distributions and maybe some percentile values also. All right, ladies and gentlemen, I'll stay on the line for a couple minutes. If you have any questions, if not, have a good day. We'll wrap up Math 115 in 2 days on Thursday. Just keep in mind the due dates for the various remaining assignments. And just try to get those done by no later than, like I said, May 5th. They have to be done. All right, have a good day.